All right, so far we've talked about the differential elements, both phase and ground. But now let's talk about overcurrent elements. And more specifically, we're going to take a look at what we need to consider when setting phase, instantaneous, and inverse time overcurrent elements. Now, before we do that, though, I want to highlight one point about differential elements, and that is that since they are differential, they only pick up for faults inside the differential zone. That is, if we set it properly, of course, they will not trip for faults outside the differential zone. In this case, of course, the transformer for the case of the phase differential element, or just the low side winding for the case of the ground differential element. Now, for overcurrent elements, however, again, this is not the case. They can, and often will actually, trip for faults that are not internal to the transformer. Now, because of this, we need to be careful on how we set them such that they only trip for faults inside the transformer, or if they were to trip for faults outside of the transformer, we need to make sure that they coordinate with the relaying on other parts of the system. Now, because of this, then we need to not only consider the transformer itself, but also what's around the transformer. Now, let's first start discussing the phase inverse time overcurrent element. Now, this is an overcurrent protection element that has an inverse characteristic. So let me actually switch to the blackboard, and I just want to have this a blank blackboard, and let me actually put a pair of axes over here. And let's draw in, let's do red. So this is going to have an inverse time characteristic like this, where this over here is current and this is time on the y-axis. So again, this has what we call an inverse characteristic. That is, the higher the current, the faster it will trip, and vice versa. Now, this element, as it relates to transformer protection specifically, is set to protect both for overload conditions on the transformer, in other words, for unfaulted conditions, but conditions for which thermal damage might happen due to it being overloaded, and it is also set to trip for fault conditions that will cause mechanical damage to the transformer. So we're going to set it again for protecting against both thermal damage for overload conditions, but also for fault conditions that might cause mechanical damage to the transformer itself. Now, these elements are set with relatively sensitive pickups. That is, its pickup is usually much lower than the available fault current. But remember again that this is set low because it needs to detect overload conditions and not necessarily fault conditions, although of course it will trip for fault conditions as well. So first, let's calculate what the pickup of this element might need to be. So when I say the pickup, I mean the current at which it will start timing. So this point over here, this is going to be our pickup. Now again, here in our example, we have a 100 MVA transformer. So we need to set the pickup of our element higher than this, so higher than 100 MVA, in order to allow the transformer to be loaded to its full rating without tripping. But this is usually going to be much lower than fault current levels, for example. Now, a typical setting is 150% of the maximum rating of the transformer. Now, in this example, our transformer, again, is rated at 100 MVA. And for the sake of this example, we're going to assume that the transformer has only one rating. But just remember again that we need to set this element based on the maximum current that the transformer can withstand. Usually you'll have multiple ratings. You'll have the OA rating and the FA rating, the forced air rating. And so you need to consider the maximum rating of the transformer. Again, for this example, we're just going to use 100 MVA. All right, so what I want to do now is let's calculate the pickup of our 51 PER phase inverse time over current element. And again, we're going to be using a 150% margin or 50% margin. So we're going to set it at 150% of the maximum rating. So we can calculate this as follows. Remember that the three-phase power equation, which I'm going to call as three-phase, is equal to the following equation. So that's equal to square root of 3 times the line-to-line voltage times the current. So if I solve here for current, I get that current is equal to the three-phase power divided by the square root of 3 times the line-to-line voltage. So here essentially what I'm doing is I'm saying, okay, what's the full rating current? In other words, if the transformer is loaded to its full rating, 100 MVA, what's that in current? What's that in amperes? And of course, here we're going to pick which side we're using. In this case, we're going to be using the high side, which is common because you're looking into the transformer. So again, this current then is going to be 100 MVA, so 100 times 10 to the 6 divided by square root of 3 times the voltage, which in our example is 230 kV on the high side. So 230 times 10 to the 3, I get that this current, which we call the full load amps current of the transformer, that's going to be equal to 251.02 amps. So what this means is that, again, if the transformer is loaded to its full rating, 100 VA, the current that the high side is going to see is 251 amps. Now, again, I said that we want our pickup to be higher than that because we want to be able to load the transformer up to that point. So we're going to be using a 1.5 factor, so 150% of the full load amps of the transformer. So 1.5 times IFLA, which is the full load amp, that's going to be equal to 376.53 amps. Now, this is, of course, in primary amps. And if you recall, in our example, the high side CT, and let's actually go back to the one-line drawing. So this CT over here is 400 to 5. So we need to divide that number then, this 376.53 amps, by 80, so by 400 to 5. So I can take that number then, 376.53 amps, and divide that by 400 to 5. That gives me that the current in secondary amps terms is going to be equal to 4.71 amps secondary. So this is what the pickup of our phase inverse time over current element is going to be. Now again, this is 150% of the full load amps of the transformer. So essentially we're going to set it 50% higher than the absolute maximum current that this transformer is going to see. That 50% is just simply margin above the highest current that the transformer is going to see under normal operations. Now in this curve, which again we call the inverse time curve, we have the pickup, which is over here, but we also have what's called a time dial setting. And that what it's going to do is it's going to shift the curve either up or down. A higher time dial will shift the curve up, which means that it will take longer to trip, and a lower time dial is going to shift that current down. So again, that's going to be what we call the time dial. Now the shape of this curve is dependent on what we call the curve type, and we're going to have several curve types in modern microprocessor based relays. So you might have like an inverse, an extremely inverse, moderately inverse, short time inverse, etc. There's several types of curves, and what you need to do is you need to pick the one that most closely resembles the characteristic of what you're trying to protect. So if you're trying to protect a transformer that has a damage curve, which we're going to see here in a second, you have to select that curve type to be something similar to that so that you can closely fit the curve underneath the damage curve. Now the other thing is, and again we're going to see that here in a second, is that you need to coordinate this with high side and low side overcurrent elements. So you want to pick a similar curve type so that coordination is a little bit easier. All right, so what I want to do now is I want to go to the Etab model that I built that is essentially the same substation that we've been using for our examples. So again, we have this 230 to 13.8 kV substation, and I actually built an Etab model that represents this substation. So let's go into that Etab model. And again, in here, this is basically that same substation, but this is actually modeled properly. So the transformers are modeled, the loads on the feeders are modeled, and I've actually gone ahead and modeled the relays as well. So again, we have our high side CT over here, our 100 MVA transformer over here, and we're going to use this CT, the current that CT is reading, for our overcurrent element. So what I've done here is I've created what's called a TCC. This is a time current curve for this transformer. And let me actually just zoom this over here so we can see it a little bit better. Let's zoom in a little bit more. And let's move this over here. All right, so again, this is what we call a TCC, a time current curve. And essentially what we're going to do here is we're going to plot the phase inverse time over current element in this plot, and we're going to see how we can select both the time dial and the curve type for our overcurrent element. So I have a couple things over here, and notice over here that this is essentially just part of the system, part of the substation that we have over here. So here we have the entire substation, the transformer, the 13.8 kV bus, and the feeders. What I've done here is I've essentially selected just this transformer, this part over here, the main breaker, the bus, the 13.8 kV bus that is, and then one of the feeders. All of the other feeders, I'm going to assume that they're going to be set the same. So if you look at this Tcca over here, this is essentially just a part of that power system. And we do that in Etab, just so that we don't have to show the entire system. We can just show the part that we're trying to coordinate. But again, so we're going to implement a phase over current element, phase inverse time over current element, using this high side CT that we're going to use to protect this transformer. Now, like I mentioned, we need to coordinate that with the low side protection over here. In this case, this feeder 1 relay and this curve that you can see over here, which is also, of course, an inverse time over current element. That one is for the feeder. So I've shown that over here just so that we can show that we need to coordinate our overcurrent element for the transformer with that feeder protection as well. The other thing that I have here is this curve over here, which is actually the damage curve for the transformer. This is essentially a model of when the transformer would get damaged. In other words, currents above this line over here would cause damage to the transformer. So when we select our time dial, we want to be below that so that we're protecting the transformer against overload conditions. Now I have another thing or another point over here, which is the maximum current of the transformer, the 251 amps that we calculated before. This is the full load amps of the transformer. And then down here we have what we call the inrush current of the transformer, which we're going to talk about here in a second. So again, I've modeled my 487E relay over here, and what I can do here in Etab is I can go inside of that and I can say I want an overcurrent element that's a phase element. Just to start, I'm going to select a U3 curve. This is one of the curve types that you can use. Now you have multiple options over here. All of these options are available in the 487E relay and all the SEL relays for that matter. In here, I'm going to use what's called an Eu3 curve, a very inverse curve. And I'm going to use that. That's very typical. I'm going to use it just because that gives a good shape that we can fit kind of close to the damage curve of the transformer. So let's go ahead and click OK. Actually, before we do that, we need to change the pickup settings. So that's going to be, again, we said 4.71 amps. So in here, I'm going to put 4.71. So now we've selected and that actually moved this over here. Let's put it over here. So we've selected the pickup of our overcurrent element. Let me actually zoom in a little bit more over here to be 4.71 amps. So we can see then that it comes all the way from here and it's actually below the damage curve of the transformer. So that's a good thing. Now notice over here that it crosses this other curve, which is for the low side feeder. We of course don't want that. We want to be able to coordinate with this curve over here. So what we're going to need to do then is raise the time dial of this curve. Now over here I can do that manually this way. And what I want to do essentially is put it somewhere around here where it's below the damage curve. So below this curve over here, but above this other curve, which again is for the low side feeder. So now if I've done this, now I have coordination. I'm both above the low side feeder protection, so I'm coordinating with that current, and I'm also below the damage curve of the transformer, so I'm protecting the transformer. So as it turns out, a time dial of somewhere around 7 is appropriate for this. Now you want to have at least 0.3 seconds of coordination time between these two curves. So again, over here on the left we have time and then we have current on the x-axis. And so you can see over here that we have seconds. We have the curve over here for the feeder around 0.5 seconds. This curve over here is around 0.6 seconds. We want that separation to be about 0.3 seconds. That's the generally accepted coordination time interval between two curves. Now in here we don't quite have 0.3 seconds, and so what we could do in a real life application is we could say, well, can we lower the time dial on the feeder a little bit and maybe do 4 on that one, and so that brings it down, and maybe that brings this separation between the two curves to around 0.3 seconds. I'm not going to go too deep into coordination here because that's not the purpose of this lecture. But again, just remember that you essentially want at least 0.3 seconds of separation between these two curves. The transformer curve, which we have over here, and then the feeder curve, which we have over here. So we have achieved that here. So again, what we did here is we did three things. We selected the pickup, which we calculated to be 4.71 for it to be 50% above the maximum rating of the transformer. We selected the curve type, which you can see over here that we were able to fit it very closely to the damage curve. And we also selected the time dial so that, again, we're below the damage curve of the transformer and we're above the feeder protection down here. So that's the three things that you need to select for a phase inverse time over current element. All right, so that's it for the inverse time over current element, the 51p element. Now let's talk about the instantaneous over current element. Now for an instantaneous over current element, essentially what we want to do is we want to say, okay, and let me actually go back to the one line. And what I want to do here is I want to say, well, I want to trip very fast for very high current magnitude faults. I don't want to wait possibly 0.5, 0.7 seconds to trip if the fault current magnitude is very high. Now the problem with that though, and the problem with overcurrent elements is that you're going to quote unquote see through the transform. So what that means is that if you have a fault down here, let's say on the 13.8 kV bus, you don't want to trip instantaneously because then you would not coordinate with anything downstream, right? Let's say, for example, there's a fault over here close into one of these feeders. You want to allow time for this element, this relay to trip first, and then you trip. So going back to the Etab model, we can say a couple of things. So one, let's actually run a fault over here, and I'm trying to simulate a three-phase fault. So I have fault type over here, three-phase. And what I want to do here is I want to say, okay, what happens if there's a fault right above, or rather right below the transformer? What's the current that the high side where my CT is, at least the CT that we're using for this overcurrent element, what's the current that that CT is going to see? So again, let me repeat that. If we have a fault right outside of the transformer on the low side, what's the maximum current that the high side is going to see? And so what I can do is I can say, well, if I know what that number is, then I can be just above it. And I can set my instantaneous overcurrent element at that level just above this number over here so that I know for sure then that this instantaneous overcurrent element will never trip for faults past the transformer. That's because, of course, the further down you go, the more impedance you're going to have and the lower the fault current is going to be. So if the fault current is above this number, that means that it's inside of the transformer or maybe somewhere in the high side between the CT and the transformer. But it's definitely not past the transformer. That's an important point. So what we can do then for our phase instantaneous element is we can say, well, I need my pickup, and let me actually zoom in a little bit more so we can see these numbers a little bit better. So again, I placed a fault here on the low side of the transformer, just outside of the transformer. And I did a three-phase current, which is going to give us the maximum current. Now the current on the high side for that fault is this number over here, 1.888 Ka, so kiloamps. So 1,888 amps. And what I'm going to do then for my example is I'm going to say I'm going to set my phase instantaneous overcurrent element just above that number, which again is going to guarantee us that we never trip for a fault outside of the transformer or further down from the transformer. All right, so we have that number, 1,888 amps. Now going back over here, we also need to consider the inrush current. Again, remember that the inrush current is essentially the current that the transformer is going to draw from the system to energize it and to magnetize it. So when you first energize a transformer, there's going to be a huge spike of current that we, of course, if we're implementing a phase instantaneous overcurrent element, we don't want to be below that because we would trip for that condition. And what would happen is anytime you first energize a transformer, you will trip back out. So you want to be also above that number. So you have two conditions now. You want to be above the maximum fault current for any type of fault outside of the transformer, which we just saw was 1,888 amps. But you also want to be above the inrush current. Now, a typical number that's used is 12 times the rating of the transformer, or the full load amps of the transformer, the OA rating. So in our case, then, we have a 100 MVA transformer, and we can easily calculate what that current is going to be, we can do the same thing. Let me actually switch colors over here. So actually we don't need to recalculate that because we calculated that over here. Again, this number 251 amps is the full load amps of the transformer. A good worst case estimate of the inrush current magnitude is 12 times that number. So 12 times 251 amps, which is roughly 3012 amps. So now again, we have two conditions. For our 50p element, we have the maximum low side current. And when I say low side current, I mean the current seen on the high side for a low side fault. So I should actually maybe just rename this. Let's say maximum high side current for low side fault. And that number was 1888 amps, or the inrush current. Inrush, which is roughly 12x the full load amps current. And in this case, that's 3012. Let's just say 3012. So essentially, this number over here times 12 gives us 3012. So essentially, we could expect a worst case current of 3000 amps spike when we first energize the transformer. And because this is an instantaneous current or an instantaneous element, we need to make sure that our pickup is above that, because otherwise we will trip instantaneously every time we energize the transformer. So going back to our curve over here, we need to set our instantaneous element over here somewhere around, let's say 3200 amps. So somewhere higher than these two numbers. And these, by the way, may vary. The worst case might be the low side current, or rather the high side current for a low side fault, or it might be the inrush. In this case, it turned out that the worst case of the two was the inrush, but you do need to consider both, because it might be that the inrush current is actually lower than the current seen on the high side for a low side three-phase fault. So you do need to consider both. In this case, again, it just happened that the inrush was actually higher. And of course, we have to go somewhere higher than that. So let's just say we're going to use a margin of 20%. So 1.2 times 3012, that gives us 3614.4 amps. And again, this is in primary amps. So in secondary amps, that's going to be 3614.4, 14.4 divided by 400 to 5, and this is amps secondary. So 3614.4 divided by 80 gives us 45. I'm going to round to 45.2 amps secondary. So our instantaneous overcurrent element pickup, then we're going to set at this number, 45.2 amps. So going back over here in the Etab model, let me actually move this a little bit left. Going back over here on my 487E relay, I'm going to have an instantaneous element that it's set to 45.2 amps. The delay is 0. So a instantaneous element. Now I'm going to combine these two curves over here. And so now I've created this combined curve. I have my 51 over here. You can see the inverse characteristic over here, and then an instantaneous over here. Again, notice that we calculated our instantaneous to be right above the inrush current. This point over here is the worst case inrush current for this transformer specifically. So we've calculated our 50p element to be just above that. Now you see here then that this curve, which is the high side 487E overcurrent element, crosses the low side current over here, or the low side curve over here. Now it may seem like then that these two relays then would miscoordinate, but they don't, because we've verified, again, the other point that I was making, we've verified that this 50p element will not see through the transformer. In other words, for a fault outside of the transformer, the fault current is going to be somewhere below this current. So we're not going to trip for faults past the transformer. We've verified that. So that's why it's important to check both for inrush and for the worst case high side current for a low side fault. Now, this element will trip, of course, if the fault is either internal to the transformer or somewhere on the high side winding. But the fact that they cross over here is not important because it's not going to actually see through the transformer. So it may look like it's miscoordinating with the low set curve because it's crossing it over here, but it's actually not, because again, we've verified that it doesn't reach through the transformer. All right, so that's it for selecting the settings for the inverse time over current element. For that one, we calculated the pickup, and then we chose both the curve type and the time dial. And then we also calculated the pickup for the phase instantaneous element. So now we have a combined both instantaneous and inverse time phase over current protection for our transformer.